write all this down. So 2.5, continuity of functions, an important section that drives the rest of the topics we cover in this class and in the future. So let's draw in these 4 different graphs. So we may want to pause and go ahead and draw those. You may know the concept of continuity, just the general idea. This one, when I draw it like that, so is that continuous? What about this one? I have like an open circle here, then it goes up here. And this one, open here, then it jumps like this. And this one goes way up on both sides like that. So there's different cases really going on here for the different graphs of A, B, C, and D. So I remember defining it, like just the idea of it when I was in grade school, that basically a function is continuous if you can draw it without lifting your pencil. Of course, now we have stylus and all kinds of other things to use, but so basically this one I can draw the whole thing without lifting. This one, to draw it, I have to lift, right? And the rest of them as well. You got to lift your pen, pencil, stylus up to do it. So those are not continuous. So that's what this one. So this is yes, and then no, no, no. So these are not continuous. So I'm going to define. We're going to define continuity now using the limits, using a limit definition. That's why we needed it, or one of the reasons we needed it in the first place, of limits. So let's define it, and I'll go back to A, B, C, and D, and we'll determine why or why not those are not continuous. So here's a definition of continuity of functions. A function f is continuous at a number c if the following is true. So we're saying it's continuous at a value, but if it's continuous for all values in an interval or on the real number line, then you say it's continuous on that intersection, or on that interval, which may be all of reals. So 1, f of c is defined. That's the first one. And when we mean by defined is, so that is f of c is a real number. So it is not undefined. 2, the limit of f of x as x approaches c exists. So you don't get a D and E or something like that. It's got to be, and that's not a one-sided, this is a two-sided limit, right? So you're not saying either sides for continuity. So you don't say a function is continuous like on an endpoint. It doesn't make sense. And then 3, the limit of f of x as x approaches c equals f of c. And that f of c is defined, right? It's originally defined. So this is really the key to all of this, is that the limit value, or the limiting value, equals the function value. So limit value equals the function value. So this is really the key, and one of the theorems basically states if you can show 3, then the function is continuous. So the key too is that this has to be in the reals. So f of c is defined. So the limit equals the function value. That's the key. All right. So let me go ahead and state that. To verify continuity, we only need the third one. We only need 3. Okay, so let's look at a few examples and determine continuity. Okay, so let's see. Okay, so let's look at this example. So determine where, like what values of x, the function is continuous. So determine of all the real numbers, what values are would make the function continuous. So you can say it's continuous everywhere except a certain value or something like that, or except an interval. Okay, all right, so let's look at that example. Actually, let me go back. I almost forgot. Let's go back to this one. So just hold on to that for a second. So so A is continuous, nice and smooth, no breaks in the graph. But B, what's the problem? What does it violate? So f of c is way up here, so it's not the function value. So is f of c defined in B? Yes, f of c is defined in B. It's defined right here. Does a limit of f of x exist in B? And the answer is yes as well. So 1 and 2 are satisfied for B. The limit does exist. It's actually L right there. Okay, but it doesn't equal the function value. So it fails 3 for B. So that's one case, is the function values are not the same. Now for C, is f of c defined? Well, f of c, and I didn't put it in there, but this would be like your c. So f of c is right there. So yes, f of c is defined. Does a limit exist? And the limit would be no. So the limit exists, it has to be both sides. So for C, it fails 2, and then therefore fails 3. Okay, so so not continuous. And then D is one of the another big problem, is the function value doesn't even exist. So f of c is not even defined. So if the function is not even defined, it's got a vertical asymptote right there. So it's not even defined at c. So it fails 1. So that could be like a question, right? I could ask you, tell me which part of the definition of continuity does the limit fail or not work, right? That kind of thing. Okay, so let's look at some algebra of functions and see what we have. So I'll try to leave it right there. So let's, given that g of x is x squared plus x minus 2 over x minus 1, determine where it's continuous. So you need to basically factor and simplify and everything. So let's go ahead and factor that. Product of two binomials over x minus 1. So it's x plus 2. You reduce it. You get x plus 2. But you can't just cancel something out. You can't just get rid of stuff. We would have to say that x cannot be positive 1. So you can't just change this and get rid of something. So basically g of x is x plus 2, just a line, except at 1. At 1 there's going to be a hole in the graph. So basically that's essentially not defined there. So this is not continuous at x equals 1, since f of 1 is not defined. So it failed 1. And then the graph let me move this down. I'll do the graph right there. So the graph is just a line of x plus 2, but at 1 there's a hole in the graph. So this is 2 here, slope of 1, up 1 over 1. All right, so it looks like this. So there's my line. However, at 1, let me do this. At 1, there's a hole right there. So here's 1. Here's x1. And so there's a hole at 1, and then that actual value would be 3. 1, 2, 3. So G, I wrote F there. I meant to write G. G of 1 is undefined. Okay, in this function. Now, this function here, the x plus 2, that is defined. I mean, if it was f of x is x plus 2, that's just a line. Of course it's continuous. Okay, so you got to be careful, that kind of stuff. All right, now let's look at another case using the same original function, but let me go ahead and define this one. Let's let h of x, you'll see what I mean, be x squared plus x minus 2. It's the same one, all over x minus 1. Okay, so that's going to be our function. X not equal to 1, and this 2 if x equals 1. So this function really is the same. You don't have to actually redraw it. It's the same basic picture as this one up here. Let me move it down, copy, move it down. But at 1, the function value is 2. So at 1, the function value is actually here. So in this case, h of 1 is equal to 2 is defined. But what's the problem? What does it not satisfy? So it's defined. Does the limit exist there? So the answer, so what's the limit of h of x? So what's the limit of h of x as x approaches 1? So as you're approaching 1 here, so you're coming in on 1 like this, you are getting a limiting value. You're getting closer and closer to 3. So the limit does exist at 3. I mean, at 1, it's equal to 3. However, does it equal the function value? So the limit of h of x as x approaches 1, we would say equals 3. So 1 and 2 are actually satisfied. But are these equal? Does the limit, so I'm going to rewrite that for you. Does the limiting value or limit value equal the function value? So does the limit value equal the function value? That's what you really are asking, assuming both exist. If one of them doesn't exist, you're done. But if the limit value and the function value exist, are they equal? That's your question. And of course, this is a no. Okay, so therefore, I meant to change that color. So therefore, h is not continuous at 1, at x equals 1. Okay, and we'll do one more. It's basically discontinuous. So if I have, and I want to talk about this function right now, throw it out there because we'll be talking about it later. If f of x is 1 over x, let's graph that thing first, because this one does come up a lot. Okay, so when you graph this thing, you get, so 1 is 1, right? But then it goes up like this, and then this one goes down like this. And then the negative values similar. So here's 1, 1, or negative 1, 1. Whoa, that thing's off like that. That was weird. Okay, so that's what the graph looks like. You need to know that graph. That needs to be one in your file system to not ever forget. So those are the graphs. So where is this continuous? So if you're asked to discuss continuity, we can see that f of 0 is a DNE. Does not exist. The function value doesn't exist. There's a vertical asymptote right at 0. You can't put 0 in there. Some of these discontinuities I want to talk about. On the first one here, this one up here, that's called a removable discontinuity, meaning if you just replace one point, it ends up being continuous. Same as this next one. That's called a removable discontinuity. All you got to do is replace one point, and then it's continuous. This one is not the case. This is called an infinite discontinuity. And so that vertical asymptote's the big problem right there. All right, so let me write out a couple things. So 1, f of 0, I already wrote that over there, so I'll put it back over here. F of 0 is a DNE. Not defined, or just say not defined. And 2, we would say the limit of f of x as x approaches 0 is a DNE as well. It does not exist. Okay, so f of 0 technically, really technically you'd say is not defined. You can also say doesn't exist, but the better way of saying it is the function value is not defined, because it isn't. It's undefined there. And then 2, you normally say the limit doesn't exist. We will be talking about infinite limits, so you can approach from the right or left, and we'll talk about how this limit, if you approach 0 from the right like this, it approaches infinity, and if you approach from the left, it goes to negative infinity. So we'll talk about infinite limits as well. As x approaches infinity, the function approaches 0, and then as you approach negative infinity, the function approaches 0 as well. So we'll get into that in this section a bit later. Okay, let's do one more before we go on to the next section, or I'm not section, next part of 2.5. Let's take a look at this example. Okay, so let's discuss continuity. If f of x is equal to x squared for x less than 1, and 1/2 x plus a half for x greater than or equal to 1. All right, so this is where I'd have you try this one. So pause this one, pause and try it. Okay, so first thing I want you to do is graph. So let me finish my statement. I guess I forgot to do that. So if f of x is that, determine or discuss continuity. Sometimes they like to say that. But I'll just say determine if f is continuous on the reals, on R. And what you want to do first, one of the ways to start right away is just start graphing these things. So you graph these individually. This is a piecewise function. We don't know if it's continuous, but it's a piecewise function. So you draw in your parabola It looks like it's open at 1, that's 1. And then it does this. And then the graph of 1/2 x plus 1/2 is here. So here's a half and then up 1. Wait, I think I did that wrong when I graphed it. Yeah, hold on a second. Let me fix this one, because I made this one up and I think I messed that up. So let me just do this. So what if you had this graph? We'll figure out. We'll go backwards. So suppose you have you go through here and you're basically at 1, 1. Then you go up 1 over 2, up 1 over 2, like that. Up 1 over 1, 2. See if I did that right. I don't remember. Okay, so there's my graph. So down 1 over 1, 2. No, I had that right. So it's 1/2 x plus a half. So you're at a half, up 1 over 1, 2. Oh, yeah, so that's right. So, and that's true if x is greater than or equal to 1. I had that right the first time. I don't know what I was doing. All right, so is it continuous? And actually, if you zoom in on this, which you don't see it yet, this has to be defined here. So you actually get this value. So you get that line like that. And so it is defined here at 1, 1. So does it meet all the criteria? And the most important one is the limit of f of x as x approaches 1 equal to f of 1. So basically, as you approach x squared at 1, is it 1 squared is 1? Answer is yes. And then as you approach, what's the function value? Well, it's equal to, here's your equal to, 1. When you plug in 1, you get a half plus a half is 1. So this is equal to 1, and it's true. So it satisfies all of those. So the limit on both sides, let me zoom in a little bit, as you approach like this, you get 1. As you approach like this, which would be this value, you also get 1. Okay, so you're still coming in on 1 there. And then the function value, what is that? It's true. So this, if this holds, it's continuous. So therefore, f is continuous on the reals. So it doesn't have to look nice and smooth. That's something else. But you would not have to actually lift your pencil to draw that. Oops, I didn't want to do that. Okay. We will go on to other topics next.